please.
Welcome everybody to Integrability Journal Club. And today I am very happy to introduce Nicolai Reshetikhin from Berkeley, who will tell us about superintegrable systems on moduli spaces of flat connections. Nicolai, please.
Okay, so thank you for the invitation. So I'll talk about two subjects that may not be so traditional in integrable community. So first, superintegrability, and second, moduli spaces of flat connections.
I don't know, but now I have to leave because it's about to start. But I
Hello?
know, for instance, how much you are in contact with the page.
Yeah, we will mute a few people.
Okay. So, bulk of this work is based on, of this talk is based on joint work with Semyon Artamonov. And so let me start with the reminder, because I mean, actually many people may know this. What is superintegrability in Hamiltonian mechanics? So for this, it's kind of instructive to have a brief tour into symplectic and Poisson geometry. So then so the notion will be more familiar. But you know, before I will do all this slightly heavy lifting, so let me first say that for physicists, I think this notion should be very familiar. Imagine that you have a complicated phase space and you have two Hamiltonians that Poisson commute. In general, you don't expect this system to be integrable. So the kind of a great scenario if these two integrals can be included in a family of n Poisson commuting integrals, where n is half of the dimension of the phase space. That's Liouville integrability. But life can be better than this. I mean, not better, but it can be different, but in some sense great. So imagine that you don't have this extension to Poisson commuting family, but instead you have something else. You have enough conserved quantities that may not Poisson commute with each other, but they are conserved quantities. And by enough, I mean, if you have two Hamiltonians, then you have 2n minus 2 conserved quantities that don't have to, that they cannot Poisson commute with each other, so, but they are conserved quantities. In this case, life is great in the sense that you still have kind of a version of Liouville tori, but this Liouville tori will be two-dimensional now, because you fixed this 2n minus 2 non-Poisson commuting Hamiltonians. And you can do this if they Poisson commute with your Hamiltonians that you started with. And so this is in two words what I'm going to talk about now. But just to give a formal definition of, I mean, maybe not necessarily formal, I mean, I gave a formal definition, but more geometrical definition, maybe more algebraic definition. So I have to go through certain stages. So first, let me remind that a Poisson manifold is a pair, a smooth manifold and a Poisson tensor. Poisson tensor is a bivector field, so it's a section of the exterior square of the tangent bundle, and it satisfies a bilinear identity, which has a very nice meaning in terms of algebras of functions. So this is a Poisson manifold. It's a geometric notion. And algebraic counterpart of this is the notion of a Poisson algebra. It's a commutative algebra. On the same space, you have a Lie algebra structure, and there is a compatibility between them, the Leibniz rule. So the algebra of functions on a Poisson manifold is an example, in some sense, typical example of such algebra, with the Lie bracket known as the Poisson bracket. And geometrically, the Lie bracket is just a very simple thing. You don't have to have PQ coordinates. You just, since you have a Poisson tensor, which is a bivector field, you contract it with the two form, which is df1 with df2. So that's the Poisson algebra. The Leibniz rule is just the usual Leibniz rule that you can imagine. And the Jacobi identity, that's exactly the bilinear identity that I was talking about for Poisson tensor. So this is the notion of a Poisson algebra. Kind of an important counterpart of this is the notion of a Poisson center. So obviously, for commutative algebra, this notion is trivial. I mean, the whole algebra commutes with itself. But for the Lie algebra structure, it's non-trivial. So the Poisson center is the kind of space of Casimir functions. It's those elements in A that Poisson commute with everything else in A. Okay, so now symplectic manifold is a particular case of Poisson manifold when the mapping, contraction mapping, so P is a bivector field, so if you feed it one form, it will produce a vector field. That's the contraction mapping. So the contraction mapping gives you a mapping from the cotangent bundle to the tangent bundle. And if this mapping is an isomorphism, if there is an inverse, P inverse, that's omega, then we have a symplectic manifold, and it's a nice exercise. I'm sure everybody did this, that the Jacobi identity for the Poisson tensor, in this case, when its P is invertible, is the same as closeness of omega. But P doesn't have to be an isomorphism. It can be just a bundle map. So it's it acts trivially on M, and then it maps fiber to fiber. So then there is a subbundle, the image of the cotangent bundle in the tangent bundle. And this subbundle is integrable in the sense of Frobenius on strata of M with constant rank. And so it's a nice integrable distribution on this strata. So there are leaves that are called symplectic leaves, and they are symplectic submanifolds. So in many ways, you know, when you will be given an associative algebra and somebody will ask you, what is the first thing you have to do with an associative algebra? Well, there is a very natural answer. So first thing I want to do is I want to understand what are the irreducible representations of this algebra. A geometric counterpart of this is if you will be given a Poisson manifold, then your first natural question is, what is the structure of symplectic leaves? And indeed, they are analogs of irreducible representations. If you will go through the kind of quantization procedure of Poisson manifolds, then functions on symplectic leaves will become, after hard work of making sense of this statement, will become endomorphisms of vector spaces of irreducible representations. So there is this kind of connection between symplectic leaves and irreducible representations, which has a long history in representation theory. It's this geometric quantization and orbit method in representation theory. That's a particular case of this correspondence when the Poisson manifold is the dual space to the Lie algebra and symplectic leaves are coadjoint orbits. So then there is a natural space of leaves.
Hi, could I ask just to give some context to physicists? Could you give some maybe examples of these constructions? Just so
I will just in a second. I will.
All right.
So the very nice case of this. Okay, I'll do it just in a second. It's on the next slide. So then you can think of the symplectic leaves, of functions on symplectic leaves, as follows. You choose some ideal in the algebra of functions, ideal, vanishing ideal, that's Poisson central ideal, and then the algebra of functions is the quotient of the smooth functions on M over this ideal. So this is an algebraic way of thinking. And in good cases, when this space of symplectic leaves is not too singular, so then the center is the algebra of functions on the space of symplectic leaves, on this quotient of M. So I already said that symplectic leaves are geometric analogues of irreducible representations. And now it's the time to give an example. So let's take the cotangent bundle to, and please interrupt me. So Nicolai, thank you for interrupting. I think it was Nikolai Gromov who interrupted, right?
Yeah, I always do that. Yeah. Good,
excellent. So please continue this, and please everybody do this. So, the cotangent bundle to a Lie group, it's a beautiful thing because by left translations you can trivialize it. So you can always think of this as G star cross G, and in local coordinates it's symplectic, so it's dp dq. And the action of the G acts on the group, G acts on itself by left and right translations. You can combine them together, you will have the adjoint action. So here we consider the adjoint action. Both left and right translations are Hamiltonian actions of G on the cotangent bundle. Hamiltonian action simply means that, if you choose any one parametric subgroup, then you will have the kind of flow lines of this one parametric subgroup. So for any one parametric subgroup, it's a Hamiltonian vector field. So in other words, local action of the group is given by Hamiltonian vector fields. When you have such action, it preserves the symplectic structure, and then the quotient is a Poisson manifold. And this Poisson manifold, it sort of looks innocent, but it's already kind of has a non-trivial structure. So because the action is Hamiltonian, so G action is Hamiltonian, there is a moment map, mu, to G star. This is really just, sophisticated version of the usual orbital moment map that brings PQ to P vector product with Q, which you think of this as a vector in O3 dual. SO3 is a simple Lie group, so it doesn't matter whether it's dual or not. There is a killing form that is identifying these spaces. So the moment map in general is just a generalization of this map. But the nice fact about this map is that once you have a Hamiltonian action of a Lie group, symplectic leaves are given by what's known as the Hamiltonian reduction. In other words, you take the pre-image of a coadjoint orbit in G star. So this is a coadjoint orbit. And explicit.
Just to make a quick precision. So your one parametric subgroup defines, if you want to cursor on a group manifold, and my tangent space defines a space of tangent vectors on this manifolds, along this curve. And this is what you define as a Hamiltonian vector field, or there is something else?
What I meant is the following. So you have G acting on some symplectic manifold X. As a consequence, you have the Lie algebra homomorphism from the Lie algebra to the Lie algebra of vector fields on X. So Hamiltonian means that this homomorphism, it goes through the Hamiltonian vector fields. So it's actually, it's a subspace here. So it goes actually to a smaller space of Hamiltonian vector fields on X. That means the Hamiltonian action.
Okay, I see. Yes, that's what I mean.
And then, yeah, okay. So in this particular,
sorry.
Yeah?
So in other words, you mean that it's just this vector field is generated by Poisson bracket with some function?
exactly. Yeah. So in our particular case of the cotangent bundle G mod G, the moment map is just given by this formula. So this is a very explicit description of symplectic leaves. And then, but you see, if G is, say, SLNR, then there could be complicated orbits. They're not closed orbits, but something like a, basically the conjugation orbits with non-trivial Jordan cells. Then you cannot really separate, say, the orbit that's going through the identity and the orbit going through the Jordan cell of biggest rank. Just the upper triangular matrix where you have identity on the diagonal and some ones on the upper off diagonal. So then you have so-called non-Hausdorff orbits. They're open, they're bad. So we, in some sense, for many reasons, we don't want to deal with this, at the first iteration of understanding of these spaces. We want to have something nice where this doesn't happen. So something nice means that let's consider those elements G which can be diagonalized. For SUN, they are all diagonalizable. But not only this, let's consider elements of G that have different eigenvalues. So this is the regular part of G. G can be diagonalized with eigenvalues lambda I such that they are pairwise different. And now there is a beautiful description of the regular part of this symplectic leaf. This is not the whole symplectic leaf, but just the regular part of it. And it is isomorphic to the following. You take a nice symplectic manifold that is the cotangent bundle to the Cartan. So that's just the cotangent bundle to diagonal unitary matrices. A Cartesian product with the coadjoint orbit O, but you have to do the Hamiltonian reduction with respect to the kind of trivial coadjoint orbit on H with respect to the action of the Cartan. Effectively, this means the following. Functions on O mod H, it's the same as H invariant functions on the orbit. In this particular case, modulo the relations that all diagonal elements should vanish. That's an explicit description of this Hamiltonian reduction. And so this regular part of the symplectic leaf, this is simply a symplectic leaf where G is in G regular, or scientifically you can say that this is just the intersection of the symplectic leaf and the regular part of our Poisson variety. Okay, so why this is nice? Because
and W is Weyl group, yes?
W is the Weyl group. Yes, in the SLN case, this is just a symmetric group. So I'm sorry, I used the wrong tool. Oh, now I used the wrong words. G is SUN. The orbit is rank 1. Rank 1 means that elements of the orbit, which are traceless Hermitian matrices for SUN, they have exactly 2 eigenvalues, distinct eigenvalues. And the multiplicity of one of the eigenvalues is 1. The multiplicity of the other eigenvalue, obviously, the second one will be n minus 1. Okay, so in this case, the Hamiltonian reduction is just a point, and our symplectic, the regular part of our symplectic leaf is just simply the orbifold. It's the quotient of the cotangent bundle to H mod Sn. In fact, in this case, it's isomorphic to the whole symplectic leaf. So in this case, the regular part coincides with the with everything else. So, but and this is the phase space of Calogero-Moser system. But for others, the kind of true phase space is bigger than the regular phase space. And the Hamiltonians, which I didn't define for Calogero-Moser system, but it's easy to do this. The Hamiltonians are simply given by the following. So we have this master Poisson manifold, which is G star cross G mod G. You can project it to G star mod G. And since you have a symplectic leaf here, so you have a mapping here. And functions on this are Hamiltonians. They are defined on the whole space. So, but the regular part of this symplectic leaf, so yes, this is the phase space for spin Calogero-Moser systems. So in fact, there is this kind of tiny question, but kind of interesting question that is, I think it's still unresolved for spin Calogero-Moser systems. What is happening on the rest of the phase space? Well, we sort of know the dynamics on the regular part of the space. But then there is a question whether the system can go to the boundary of this regular part and can leave the regular part to the singular part where the eigenvalues coincide. Probably not, but I know that it can touch the boundary. So I think these subtleties are still unresolved for spin Calogero-Moser system. I don't know what will be the kind of dramatic physical consequences of this. Probably none, but mathematically it's a curious question.
But it is important for classics, yes? So for classical situation.
For the quantum case too.
For quantum
because,
case.
Yes, for the quantum case, it has, well, we can have a separate discussion because if I'll start to talk about it now, it will take the whole hour.
Okay.
So anyone who is interested in the quantum Calogero-Moser and these subtleties, I'll be happy to answer these questions in a separate discussion.
Okay.
So, okay. So now,
so just a question, I missed it. So what's the number of particles in the Calogero model, the rank of the group?
Yes, it's n. N particles. And since it's SUN, it's in the mass center. So sum over I pi is 0, sum over I qi is 0.
And when you say it's a spin Calogero model, what is the internal?
It's just a Hamiltonian. In this particular case, it's just very naive spin Calogero-Moser system, not the one that was introduced by Gibbons. And gosh, I forgot the second person who wrote the paper with Gibbons.
Hermsen.
Yes, exactly. So this is the Hamiltonian that I have in mind. And these are the functions. These are the functions on the coadjoint orbit Hamiltonian reduction with H, in the sense that mu I is 0, and obviously these functions are H invariant.
So some of this, both the spin and the number of particles are controlled by the same SUN?
By the same SUN, yes. There is more physical system that's, I mean, more physically meaningful system version of spin Kalogero-Moser. That's sum over I less than J. Let's say Si as J, where S are spins of the same radius R plus some constant divided over sine squared Qi minus Qj over 2. So this system, it has, it corresponds to this master space. So you take the cotangent bundle to G cross G, and you have the action of G cross G on the left, you have the action of G cross G on the right, you embed G diagonally in G cross G, and you take this double quotient. And in this case, the symplectic leaves, they are parameterized by two coadjoint orbits, one for the left, one for the right. And if both of these orbits rank 1 orbits O prime, then you will get this integrable system, and it is a superintegrable system. In fact, it's maximally superintegrable, meaning that.
So how from the abstract construction I see that this is a Hamiltonian, because you wrote it just now, but is it something one can derive from what you wrote before?
Yes, so here you have p coordinates on the cotangent directions q, well, e to the I q coordinates on H, and Sn simply means that Hamiltonian is invariant with respect to the permutations.
Yeah, but how do I get this expression for the Hamiltonian? What is the calculation?
This is the second Casimir. This is trace of x squared, where x is in G that we identified with G star, and it's this G star. It's this G star. I have papers on this. So the latest one with all references is from 20. It's my. I don't remember already. I think it's 19. It's dedicated to Dubrovin. So it's easy to identify it. And it's about spin Kalogero-Moser systems on homogeneous spaces. And I consider two examples of homogeneous spaces. This is one, and the other is when you take G mod K, where K is the stable subgroup for the Cartan involution. So for example, for SUN, K would be SON.
And what about high Casimirs? Do they exist? Do they commute?
They exist, of course. You can write. You will get some, as you know, they will have the same nature as for the usual Kalogero-Moser system. So there will be some invariant polynomials in P. Just choose any basis in the space of invariant polynomials on Rn, and then every invariant polynomial with respect to the action of the symmetric group. And every such invariant polynomial extends to some kind of Hamiltonian that involves Q and spins.
But then the statement is they all commute with each other, or?
And they all Poisson commute with each other, yes.
So that's the way to see integrability in this model. That's correct.
That's the way to see integrability if this system is Liouville integrable. If it's not, if it's superintegrable, then this is what I was planning to talk about in the next 10 minutes.
Mm-hmm.
So shall I proceed, or should we have a little more discussion of collisional motor systems.
Yeah, I don't know. Maybe we can have a bit more questions, because otherwise I'm afraid we can like decouple. So maybe some other people can ask something.
Okay.
So, and in principle, you can put some representation, for example, this key, left key, right, and yes, and make.
This is all classical. This is all classical. So the only representations that you have is when you don't have even representations here. You just take.
Yeah, I actually think quantum. Actually, I think about reduction of Laplace-Beltrami. Actually, yes. Second Casimir.
Okay, in the quantum case, these are just radial parts of the Laplace operator acting on functions. So quantum case. Well, you choose some representations. Let me talk about a single representation that would correspond to this case. So choose representation V, and then Hamiltonians, quantum Hamiltonians, are radial parts of Laplace operators acting on functions on G with values in endomorphisms of V, G invariant with respect to kind of diagonal action. So G acts diagonally on. Yeah, so these are G invariant functions. So here you use representation, here you use the adjoint action. Yeah, and this representation V, it corresponds to O. And then you can choose a basis in this space of functions and so on. So these are kind of spherical functions.
Yeah. So, and once we already speak about quantum case, so the notion of superintegrability will be promoted to quantum case. So you will have bigger algebra.
Yes, actually, in this particular case, it's all explained in my paper from 2016 or something like this. It's called quantum. You see, there are two competing notions, superintegrability and degenerate integrability. I don't remember which one I used back then. I started to use degenerate integrability for good reasons. It's a better word than superintegrability. But everybody is using superintegrability, so I switched to superintegrability. So quantum superintegrability of collisional motor systems. I think it's published in Letters in Mathematical Physics, but it's on the archive.
So again, in this context, what does superintegrability means concretely? So the collision model has all the commuting Hamiltonians.
Okay, now I'm kind of, now I'll be commenting, I'm sorry. No, we have to move on. You're asking questions about the future. So let's depart from this. So now I can see that everybody knows what is a Hamiltonian dynamical system on symplectic manifold. So it's just the Hamiltonian flow line of the Hamiltonian vector field generated by X. So let's move on to superintegrable systems on symplectic manifolds. So let's assume we have a symplectic manifold M. The algebra of functions on M is a Poisson algebra. There is a Poisson bracket, which I already was talking about, and everybody knows what this is. So now I want to give a precise definition of what a superintegrable system is and what's the relation between superintegrability and Liouville integrability. So this is our friend, symplectic manifold. And consider a Poisson projection to some Poisson manifold. It's a projection, so the dimension of P is less than the dimension of M. I assume that it's surjective, so the whole thing of the P is covered by this projection. And as a consequence, the fibers of this map are isotropic submanifolds. Isotropic simply means that tangent vectors to these submanifolds, you know, they span an isotropic subspace in the tangent space, which means that the symplectic form on any pair of tangent spaces is 0. So isotropic submanifolds of dimension k, if this one has dimension 2n minus k, and this has dimension 2n. Okay, so this is just a Poisson projection with this nice property that it's onto, and so then as a consequence, the fibers are isotropic. So what does it mean in terms of, sorry, what does it mean in terms of the algebra of functions? It means that we have a Poisson algebra, and we have a Poisson subalgebra, and we have a Poisson subalgebra, so we have Poisson embedding. Easy. So that's just triviality. Now, another piece of triviality. So suppose that you have a Poisson algebra, and suppose that you have a Poisson commutative subalgebra. So we will say that this Poisson commutative subalgebra is the center of J if it Poisson commutes with everything else. And this is called the Poisson center. How to say that we have a Poisson center geometrically in terms of the Poisson manifold itself? Again, it's very easy. So suppose that we have dimension here 2n minus k, here the dimension k, then generic fiber, it will have dimension 2n minus 2. It doesn't have to be connected, it can have several connected pieces, but each connected piece should be a symplectic manifold. So that means that generic fibers of this Poisson projection are unions of symplectic leaves. And we assume that the base of this projection is a trivial Poisson manifold, trivial meaning the Poisson tensor is trivial, and this corresponds to the subalgebra being Poisson commutative. So again, this is...
Ola, one question. Did you mean 2n
yes?
minus 2k?
2n minus 2k, yes, of course. Thank you. Great. So these two pieces are complete triviality. It's just kind of, I recycled basically the notions that we already had. But now let's combine them together. So let's assume that we have...
Sorry, maybe we will pronounce that I is a set of Hamiltonians and J is a set of integrals of motions.
It will come. But so far, this is just... So far, there is no physics. It's just a pure algebra. So okay. Here you have the algebra, and you have its center.
Yeah, sure.
But it's coming. What you said is absolutely true, and this is what's coming next. But first, let's just massage this a little bit more. So algebraically, suppose that we have an algebra, and we have a Poisson commutative subalgebra. So what do we have in the algebra itself? We have something that's called the centralizer of I in A. In other words, this is the set of all elements in A that Poisson commutes with everything from I. Okay? For any Poisson commutative subalgebra, we certainly have this notion. And for any Poisson commutative subalgebra, the centralizer is also a subalgebra. So we have these embeddings. Dually, in terms of functions, on the top we have a symplectic manifold. Since we have an embedding of a Poisson subalgebra J, so it means that we have a projection to some Poisson manifold whose fibers are symplectic leaves, and we have the second projection. So this is for any Poisson commutative I in A. It has nothing to do with integrability yet. I mean, it has to do with integrability because if I is not, so if our Hamiltonian is in I, if there is nothing else, then it's not integrable at all. If there are some extra Hamiltonians, then we can say a little bit more about the dynamics. But this is neither Liouville integrability nor the superintegrability. So now let's look at what is the maximal dimension of B. What is the maximal rank of the Poisson commutative subalgebra? And just I will use the notion of rank. So rank of a commutative algebra, this is simply the maximal number of algebraically independent elements in A. So it's a very natural notion. It's just that if A is the algebra of functions on something, then that's the dimension of something. Sorry, was it a question? Okay. So what is the maximal dimension of B? Well, naturally, it's the case of Liouville integrability. Maximal dimension is n, which is the dimension of m over 2. And in this case, we have an embedding of the maximal Poisson commutative subalgebra in our algebra of functions. And dually, in geometrical terms, we have a projection from our symplectic manifold to the base, and it's a Lagrangian fibration in the sense that generic fiber is the union of Lagrangian submanifold, so it's a Lagrangian submanifold. Lagrangian means maximally isotropic. So this is the Liouville integrability, and these fibers are Liouville tori. When they are compact and when non-compact, we can still call them tori, but they're pieces of real line. So this is fine. But now, what if the size of this commutative algebra is smaller? So let's just fix our Poisson commutative subalgebra of Hamiltonians, and let's look at what is the typical size of the centralizer. Say, what does it mean? What is the chance that there is an extra independent function in A that Poisson commutes with our commuting family of functions? Tell me. In terms of probability theory, this is a very rare event. So typically, the centralizer of a Poisson commutative subalgebra is the algebra itself. There is nothing else. Because if there is something else, then we have an extra integral of motion. Then our dynamics sort of can be refined by fixing the level of this integral. So there is a small theorem that describes the maximal possible rank of the centralizer. So maximal possible rank is 2n minus k, where k is the rank of our algebra. And geometrically, it's the maximal possible dimension of P. So now I want to define a superintegrable system on M as a structure that we have on our symplectic manifold. that allows for a superintegrable dynamical systems, So here's the definition. A superintegrable system on our symplectic manifold is the following. It's these two projections that I was talking before. So with an extra condition that the dimension of this intermediate Poisson manifold is maximal possible. Algebraically, it means that we have a commutative subalgebra with, so it's a Poisson commutative subalgebra with maximal possible centralizer. And that's a non-trivial property. So, as I already said, for symplectic manifolds, such systems, such structures is a rare event. And when k is equal to n, this is the Liouville integrability. In this case, p is equal to b. In this case, 2n minus k is equal to k. Okay, any questions about the definition?
Can I make a small comment? Actually, we are already around the coffee break, so it would be nice if it's possible to make coffee break more or less now. It will be good. Yes. Okay. Then two very quick questions about the definition of superintegrability, and we will go to coffee break.
So I mentioned before that example of these systems can be also embedded in your previous example, right? It's just when eigenvalues are degenerate. Is it correct or?
Okay. In the quantum case, superintegrability means the following. So first of all, Liouville integrability. Say, on an n-dimensional configuration space, we have n independent commuting differential operators. And typically, in the Liouville case, not typically, but always, the degeneracy of the spectrum is stable when the Planck constant goes to 0. Well, since we're physicists, so I'm pretending to be a physicist, of course, in the relative units. Superintegrability. It's when the dimension of the eigenspaces, the spectrum is degenerate, it behaves as some negative power of the Planck constant. And this negative power is half of the dimension of the fiber of P2. So in this diagram, the kind of semi-classical degeneracy of the spectrum of the corresponding quantum system is encoded. Okay, did I answer your question?
Well, I was actually asking about something more basic. Before you had this example of the system, right? And it was built on this eigenvalues.
Yes.
And of your metrics. So I don't mean.
You mean
Hamiltonian, but the particles were eigenvalues, right?
Okay, you mean what happens in the quantum case when this Qi is equal to Qj?
The question was whether there is an example like similar to what you had before, When it
Yes.
is superintegrable rather than Liouville integrable.
Oh, yes, of course. You see, the point is that all these examples, this, they are all superintegrable. So this one is superintegrable when this one is superintegrable when the rank of the orbit is greater than 1, and this one is always just superintegrable. They are not Liouville integrable.
But so if I just think about this Hamiltonian as describing dynamics of n particles, what should I do with this system? In which regime it is superintegrable and in which it is integrable?
Both of them are always, if you fix the coadjoint orbit here, if you fix the coadjoint orbits here, this radius of the spin and this constant c, they correspond to they are fixed by the choice of O and O prime. So it's just, they're superintegrable, period. You have no choices. So it's a system of particles. You have obvious kind of n minus 1 Poisson commuting Hamiltonians, which are polynomial in P. And then you have some other conserved quantities that are more complicated, but they exist. The Poisson brackets are kind of close between each other, and they describe the sort of degeneracy of the spectrum.
So it's because there is some fine tuning between this like dimension of the spin and number of particles?
No.
No.
It's just the number of particles is fixed. It's okay. In the quantum case, if in the quantum case, if it's a non-spin system, you don't have any spin degrees of freedom. So then it's just Liouville integrable. So then you have n minus 1 Poisson commuting Hamiltonians on 2n minus 2 dimensional phase space, or you have differential operators on Q, kind of usual commuting. But if you have spins, the Hilbert space is bigger, but the number of Hamiltonians is the same. And so so you have big degeneracies of the spectrum.
Mm.
And you cannot really say, there are people who believe that if you have a vector space or a Hilbert space and you have, say, enough commuting operators, then you have an quantum integrable system. I think this is a little bit naive in the sense that that every matrix can be diagonalized, and the projections to eigenvalues they always commute. It doesn't mean that every Hamiltonian is integrable. You need more structure to say that there is an integrability.
Can I ask a question?
And yeah.
Коля, like XXX, spin 1/2 in the infinite volume for the infinite length of the lattice has Youngian symmetry. So those Youngian generators, first it's infinite dimensional. Second of all, Youngian generators commute with the Hamiltonian, but do not commute with each other. Is this related to superintegrability?
Which Hamiltonian you have in mind?
XXX spin 1/2 for Heisenberg with a plus sign. Nearest neighbors interaction.
And, which Youngian?
1929.
Which Youngian do you have in mind?
Youngian based on SU2.
I don't know if there is a symmetry like this.
Well, okay.
The Heisenberg magnet, its Hamiltonians come from G-invariant functions on the Youngian.
Hamiltonians
that are commuted.
Well, generators of Youngian commute with Hamiltonian.
Oh, you mean some kind of more sophisticated internal symmetry? So is this the question basically about there are local conserved quantities in let's say in quantum field theory, and there are non-local
non-local.
conserved quantities.
Non-local, of course.
Yes. So I think the non-local, the presence of non-local integrals, that's an indication of superintegrability.
All right, thank you.
In the infinite dimensional case, it's all kind of hidden because, you cannot really say that you have infinity over two conserved quantities, and this is exactly the right number of conserved quantities, local conserved quantities. So for example, I would say that if you have a quantum field theory that's integrable, and if that's sort of Liouville integrable, then in this quantum field theory, particles shouldn't have internal degrees of freedoms, and the scattering amplitudes should be just functions of rapidities if it's a relativistically invariant theory. But if there are internal degrees of freedom, then sort of it's a candidate for actually superintegrability.
Okay, at this point, let's turn off the recording and go for coffee.
How many minutes we have for coffee?
Well, it's not fixed. It depends on coffee break discussion. So, but typically, I don't know, 10
minutes, let's see.
10 minutes, okay. So should I switch off the...
Okay.
Actually,
Yes,
it's
so
on the next slide. That's right. So should I start?
Yes, please.
Okay. So now I'm answering this question exactly. So this is a definition of refinement. Suppose that we have two superintegrable systems such that Hamiltonians, I will call elements of I Hamiltonians, and I will call elements of J, the centralizer, integrals of motion. So suppose we have two superintegrable systems such that I1 is a subalgebra of I2. So then automatically we have these embeddings. So then J2 will be slightly, whatever commutes with I2 will be slightly less than whatever commutes with I1. So, and we have these embeddings. In this case, we will say that this superintegrable system is a refinement of this superintegrable system. In which sense it's a refinement? Because here you have, yes, let's say that here the rank is K1, here the rank is K2. So our assumption is that K1 is less than K2. Then this one will be bigger J1 than J2. But then level curves, level surfaces of J1 will be, because it's bigger, will be submanifolds in level surfaces of J2. In other words, say, imagine that K2 is 2. So this is all we have, the torus. And imagine that K1 is 1. So then we know that on this torus, there is a periodic trajectory that doesn't cover all the torus. It's really periodic one-dimensional trajectory. And that's what we know about the dynamics of J1, if there is this superintegrable system. So if you just have this information, you have no idea whether trajectories are periodic or whether they span this two-dimensional torus. But if there is a refinement, then you know that every trajectory is periodic. So every trajectory here is periodic if there exists a refinement by I1. So I don't know, I hope it's convincing. And in particular, if K2 is N, so a particular case, K2 is N, K1 is 1.
Yeah.
This is the maximal superintegrability. And in this case, you can say that all trajectories are periodic. And this is actually exactly happening for Calogero model system. This is the result of Wojciechowski from, I think, from the 80s. So I will say a few words about the notion of the history of superintegrability. So this is Wojciechowski. So this is the reason why superintegrability is a reasonable notion. It really refines the dynamics. Even if you have a Liouville integrability, you can say kind of a lot about. I mean, that's a great stuff. It means that sort of if you did all the steps, you solved the equations of motions explicitly. But you still don't know whether the motion on the Liouville tori is ergodic or it can be contained to a smaller subtorus. Superintegrability tells you exactly about this, so that it can be. So now, just the same as for integrable systems, you have a notion of equivalence. So the same for the superintegrable systems. If you have two superintegrable systems that are connected by a diffeomorphism, then we say that these systems are equivalent. So I described the structure of superintegrability. Sorry, the definition of superintegrability. But not superintegrability yet. Superintegrable. I defined what a superintegrable system is. And now I want to be very mathematically precise. I want to define superintegrable Hamiltonian dynamics. And I want to separate these two notions. Because superintegrable structure on a symplectic manifold, it's already a rare event. I mean, you have to look for these structures. And Hamiltonian dynamic superintegrable dynamical system, this is a very lucky event when your dynamics fits into a superintegrable structure. So the definition is very natural. It's a superintegrable system. So if your Hamiltonian is in one of these Poisson commutative subalgebras that have the centralizer of the maximal rank. If there exists a superintegrable system where H is one of the Hamiltonians. So this definition is trivial. I think there is nothing more to discuss. But now there is a theorem. That's the Liouville theorem for k equals 1. And it was extended to superintegrable systems. And by Nichorashov, he was a student of Arnold. This paper is from 1970s, 76, I think. And right. So here I should say a few words about the history. So so he kind of formalized what was known before. What was known in examples before. And the first example is the Kepler system. Well, we all know who invented Kepler motion. So in here, it's due to the fact that there are two natural conserved quantities for the Kepler system, the orbital momentum and the length vector. It's called length vector, which is a little bit unfair because it was known before. The first person who invented this conserved quantity, he's a Swiss mathematician. He was a Swiss mathematician from Basel. Unfortunately, his last name escaped me. It starts with H. He was a master of stellar mechanics, and actually he was a cousin of Euler's mother. So there is a connection to Euler here. And as Euler, he spent some time in St. Petersburg, I think, but short time. So so it's called length vector because Lenz actually invented quantum version of this vector, and it's known as Runge length also vector. So the quantum version of this is the hydrogen atom, and I mean everybody knows in this audience that the spectrum of the hydrogen atom, the eigenvalue that's 1 over n squared, its degeneracy is n squared, maybe n plus 1 squared. And so you can see that if you put h squared over here, then as h goes to 0, the degeneracy behave as h to the minus 2. And that's exactly superintegrability. So here I should mention the names of Pauli and Fock. And after kind of this, there was a big break. And then the next examples were discovered by, there were several names on this article. I remember only Smorodinsky and Winternitz. Smorodinsky, for him, it was sort of an episode. Winternitz kind of has some many other works that continue this line. So there were many other examples. So then there are people who contributed this as well. So I should mention the name of Feher. And I didn't mention many other names, but it's kind of a big subject in symplectic geometry in particular. So anyway, so let me
just
go to the subs. Yes.
Just to stress, so for you, it is one of the most important properties of superintegrability on quantum level. This divergence, degeneracy, so this behavior of
absolutely, yes. If you have just a Liouville integrable system, meaning, say, I'm talking about differential operators on the configuration space. If these differential operators, their symbols, I mean, if they're commuting, then their symbols will be Poisson commuting functions on the cotangent bundle to the phase space, so functions of P and Q. The spectrum of these differential operators is always stable as h goes to 0. You cannot have, I mean, the infinite degeneracy would be some kind of weird property of the classical system. It cannot be more degenerate than the classical system. And by degeneracy of the classical system, well, I basically mean so something like this, that you have PQ coordinates, you have some strange level curves of your Hamiltonian, and then the maximal degeneracy here is 4. Sometimes it's 2. So something like this.
Yeah, but at the same time, it also should be visible on level of algebra of operators somehow. Like you have here.
Yes.
So now you will have something in universal enveloping algebra, something bigger than just Casimir's if we speak about collateral.
Exactly. So that's exactly why I wrote this paper, the quantum degenerate integrability of Kaluza model systems. I mean, it's all there. It's sort of, it's not all there, but what I'm trying to say about it, it's all there.
But you don't build explicitly this this extended algebra, yes?
You see, algebras, they are kind of creatures with characters. So what you want to typically do with algebras is sort of to describe them. To give them explicitly with generators and relations can be a pain in the neck. And, you know, unless it's an algebra with this property that it has finitely many generators and finitely many relations, you might not be able to do it, say, if it's not a Noetherian algebra. But you can describe it as some algebra of invariant operators or something like this. So what I did in this case, I described it. I didn't build it explicitly in terms of generators and relations. So anyway, so I mean, this is all, you know, as our lives, this is all work in progress. So I think there is no final answers in this paper, but there are some answers. So I think it's, if you are interested in these questions, it's probably worthwhile reading and then throw it away and do something new. So what I want to say about this integrability, this is all just the same as in the case of Liouville integrable systems. Flow lines of this Hamiltonian vector field, if H is one of the Hamiltonians, they lie in connected components of the Liouville tori. And then these are the angle coordinates. So the flow lines generated by maximal commuting set of Hamiltonians, they define an affine coordinate system. Affine coordinate system, it's just the same as in Liouville theorem. Simply means that it's a coordinate system where coordinate transformations are translations and linear transformations. So I just want to make a brief comment. The case when H is generated by, say, n Hamiltonians, this is a very lucky case of a free algebra generated by H, kind of free commutative algebra. Typically, this is not so nice. Typically, you have some kind of huge number of elements that generate huge free commutative algebra, but then you have to quotient by relations where there are n minus n independent relations. So that's a typical structure. So in here, you don't have the kind of canonical generators. So here the spectrum of I is Rn. It doesn't have to be this way, or at least it's a subspace in Rn. So here the spectrum, so these are independent, but you can choose them differently. You can choose something else, also independent, and then you really should consider this as coordinates on this kind of on the space that's this space of values of classical integrals, your kind of classical version of the spectrum. Okay. So now, just as in the Liouville theorem, every connected component is isomorphic to the product of a torus and Rn. If the system is completely non-compact, there is no toric component, there are only Rn's. So for example, if you have Kaluza-Moller system with 1/sinh squared potential, then it's Rn. When you have a Kaluza-Moller with sine squared potential, then it's Dn. So flow lines, this is the main thing. You know, this is the kind of dynamics in the angle variables. This dynamics is linear. And so this is really the most important thing. So obviously, kind of, you know, if you're a geometer, then great, this is the answer. But say if you're an kind of in mathematical physics, then you naturally want to ask the question, how to find these coordinates. And this is the non-trivial part. This is where you have the kind of hard work. So construction of angle variables. So then in the Liouville case, in the action angle coordinates, the symplectic form is canonical. In other words, in the Liouville case, action angle coordinates are Darboux coordinates. In the superintegrable case, they are not Darboux coordinates. So there is this piece that's to the Darboux piece. But then there is another one where omega c is the symplectic form on the fiber of P2. So it's, oh. Hello? Can you hear me?
Yes, we can.
It's just that my laptop started to get to freeze, and it's I don't know what this is. Maybe I'm overloading it with too many files. So remember that we have these projections, P to B. Fibers here are symplectic leaves. So it's the symplectic form on these symplectic leaves. So this is sort of the action angle theorem for the conserved quantities. And just repeating what I already said, such dynamical system has 2n minus k conserved quantities, and level surfaces are invariant submanifolds, and these are the independent elements from the centralizer, and I is the subalgebra of Poisson commuting Hamiltonians. So, okay. So this is the big, this is the end of chapter 1. I explained what superintegrability means. And I hope I convince you that this is an important notion, just as important as Liouville integrability.
Yeah, certainly. And can I ask us a question before we go further? How much time do you need? What do you think?
Well, let's see. Let's look at the number of pages. So I covered 11 pages. I had 31. So if I really want to explain everything that I plan to explain, then probably another seminar. But I can make a kind of shortcut, and I think I can explain it in 10 minutes.
Oh, that will be super great. Great.
Okay, so then let's skip the kind of details about the moduli space of flat connections. I think many people know this. So what is important about this? It's important that the moduli space of flat connections, it's the following. You take connections on a principal G bundle over sigma. Let's assume that this principal G bundle is trivial, so connections can be considered as one forms. Flat means that the curvature of this connection is 0, and we mod them out by the gauge group. It turns out that there is a natural symplectic structure on this space, because this space can be considered as the Hamiltonian reduction of this space with respect to the Hamiltonian action of the gauge group. And this is the paper by Ati and Bot from 1983, in case when the boundary is trivial. When the boundary is non-trivial, similar arguments gives the Poisson structure on a finite dimensional Poisson manifold. That is our moduli space. So symplectic leaves of this Poisson structure are gauge classes of flat connections with fixed conjugacy classes of holonomies around each connected component of the boundary. Now, a finite dimensional model for this is just the character variety. So you take the representations of pi1 of sigma, the fundamental group of sigma, to G. So if you just take these representations, this is called the representation variety. It doesn't have a natural Poisson structure. No natural Poisson structure. On the character variety, because it's the same as the moduli space, there is a natural Poisson structure. It doesn't mean that this space doesn't have a nice Poisson structure that can be nicely described. In fact, it does. And that's the paper by Fogg, a different Fogg, related but different, Fogg and Rossley from 1990s. But I'm just mentioning it, I'm not going to use it. So for these are finite dimensional manifolds that can be easily described. So this is just when m is not 0, then you just take g to the appropriate power, mod the conjugations. If m is 0, then you take the holonomies around the fundamental cycles, but then you have one more relation. So it's a subvariety in g to the power 2g mod the adjoint action of g. So then one can find a description of the Poisson structure on these moduli spaces in terms of kind of Wilson loops, if you want, or Wilson graphs. On sigma. So for this, you have to color the graphs by vertices by invariant tensors and edges by representations. Finite dimensional, not necessarily reducible representations. So then if you choose a basis in each of these representations, then you define the graph function as the contraction of holonomies along edges with invariant tensors corresponding to vertices. And in this particular case, it just, if you choose a basis, then it's just this kind of state sum, if you want. So the natural proposition, that's the kind of Wilson graphs property, generalizing the notion of Wilson loops, that these are gauge invariant functions. And then the second property, again, it's just the property of flat connections, that if the connection is flat, then, and if gamma 1 can be continuously deformed to gamma 2, then the corresponding graph functions coincide. Here's an example of continuous deformations. You can move the components, one component through the other. And then there are some equivalences between graph functions that are just properties of invariant tensors. And then there is a nice theorem that says that graph functions, they span the ring of polynomial functions. I don't know who first invented this theorem. I think in our paper with Anderson and Mattis, we reinvented it. It was known before. So this, yeah.
Also, and you used representations on edges, yes, as parameters.
Yes.
So here you should choose all possible representations to.
No. Yeah. You mean in this theorem?
Yeah. For all this, you should choose all possible graph functions with all possible intermediate.
No, there are lots of dependencies. So what I mean is, yes, if you choose all possible invariant tensors, all possible graph functions, all possible representations, these graph functions, they span the ring of polynomial functions. The basis is much smaller, but it's difficult to describe. This is one of the problems, central problems in invariant theory, how to describe such basis. It's easier to construct the set that span this space.
Okay. Thanks.
Okay. And then the Poisson structure in terms of Poisson brackets between graph functions, it's given by this expression. So here, epsilon is the relative orientation of the graphs at the intersection point. So it's 1 if they intersect like this, -1 if they intersect like this. So here we use the orientation of sigma and gamma 1 and gamma 2. Otherwise, this number is not defined. So the surface should be orientable here and oriented. So then this star means that we encircle, we insert here a small chord colored by the adjoint representation near the intersection point. Because the connection is flat, it doesn't matter where you insert it. It's just in some small neighborhood of the intersection point so that you wouldn't touch some other singular points. And the invariant tensors that you put there are simply representations. These are mappings from G to endomorphisms of G. Endomorphisms you can write like this. So P can be considered as an element of this space. And then it's G invariant because P is a homomorphism.
Also, because it is flat, you can deform these edges. Yes?
Exactly, that's what I said. Yes.
So in principle, you can remove it all intersection.
No, not every intersection you can remove. For example.
Yeah, not every, but in principle, you can remove some of them, and you can add some of them if you make deformation.
Absolutely, yes, absolutely. But you cannot remove all of them if the topology is non-trivial. So, for example, on a torus, if the two cycles are kind of independent, then there's definitely an non-removable intersection point.
Yeah, I mean, yeah, but object is defined correctly, so it's self-consistent in this sense.
Yes, so this bracket is independent.
Yeah.
It's a theorem, independent on continuous deformations of gamma 1 and gamma 2. And it was first, so for loops and for G of the type SLN, SON, SPN, that's the Goldman bracket discovered by Bill Goldman. and for others it was found later. So, and of course this, you know, perturbation theory for Chern-Simons heavily uses this notion of chords. Do I still have 5 minutes?
Yeah, sure. Take your time.
Okay. So now Poisson commutative subalgebras. So because of these brackets, because these brackets are entirely kind of depend on the intersections of corresponding graphs. So let's consider two non-intersecting cycles, C1 and C2. And let's consider the graphs that are contractible either to C1 or C2. So it's something complicated like this, some kind of belt graph that you can contract to one of these contours, C1 and C2. I'm just giving an intuitive definition. I hope it's clear what I mean. So then the corresponding subalgebras. So these are generated by by F gamma for such gamma. So they will be Poisson commutative simply because you can deform these graphs in such a way that they will not intersect. So if you have any two graphs, gamma 1 and gamma 2, that are contractible to this contour, to C2, then you can separate them a little bit, and then they will have zero intersection, empty intersection. So that's why this algebra, the algebra of such graphs, is commutative. And of course it will commute also with the corresponding subalgebra for C2. And so as a consequence, we have the subalgebra for such Poisson commutative subalgebra for any non-intersecting, non-self-intersecting curves C1, Cm. And of course, it doesn't depend on the curve. The subalgebra depends on the topological class of this collection of curves. So this will be our Hamiltonians. Okay, so, but these are the Poisson commuting Hamiltonians on a Poisson space, because I didn't require that the boundary is trivial. So now the Poisson center of the algebra of functions, and this is kind of well-known result, it's spanned by graph functions contractible to boundary components. So you draw the curves parallel to boundary components, and then these are the graphs that can be contracted to such things. Very good. So then connected components of level curves of Casimir's are symplectic leaves in our Poisson manifolds. Equivalently, you fix the conjugacy classes, as I was mentioning before, and it's almost equivalent, but again, these are the subtleties that we can ignore now. So very good. So these are the Hamiltonians. And then let's define the subalgebra J, C, as the subalgebra generated by graph functions on sigma minus these curves. So you just remove these curves from sigma, and then whatever graph you can draw on the remaining part of the surface, take the corresponding graph functions, and these are the elements of JC. And our result with Artamonov is that this Poisson embeddings is actually a superintegrable system. In other words, this subalgebra is the centralizer of the Hamiltonians, and there is a balance of dimensions. The dimension of the spectrum of B plus the dimension of the spectrum of J is exactly the dimension of the phase space. This is the main result.
Nicolai, this is again, this subalgebra is commutative, right? Subsector.
Which one?
I mean, the that you define here on the centralizer. The subalgebra itself here is completely.
So this is Poisson commutative.
Yes.
This is not. So the mapping class acts on these superintegrable systems, making many of them equivalent. For example, if you take a torus with one puncture, if you take Hamiltonians corresponding to this cycle, there is a mapping class group element that maps it to the Hamiltonians corresponding to this cycle. And this is the correspondence between, say, relativistic spin Calogero-Moser system and relativistic spin Ruizinars. I should say that if you restrict to regular parts of the symplectic leaf. Okay, so I already started references to specific integrable systems. So Calogero-Moser system and spin Calogero-Moser systems, we already discussed them. So this is a particular case of this, and this is the linearization of the case when you have a torus with one puncture and you have flat connections on this surface. Linearization means the following, that in this case, the moduli space is just G cross G mod G, where G you can choose two fundamental cycles on this surface, and that's the images in G. So these are the representations of pi1. And linearization means the following. You can linearize the Lie group to G, and then you can use the killing form to identify G with G dual, and as a result, this modular space linearizes to T star G mod G, and that's exactly the 1 and 2. And relativistic spin Calogero-Moser systems, so as I mentioned, they live on these surfaces. Ruizinars-Schneider systems, they live here. They simply correspond to diagonalization of different holonomies. The Calogero-Moser system correspond to diagonalization of this holonomy, and spin Ruizinars correspond to diagonalization of this holonomy. Well, naturally, if you have one puncture, you can ask, what if you have n punctures? So then the generalizations will be actually Liouville integrable systems. When the corresponding conjugacy classes that you put here are of rank 1. And these are the works, I mean, they studied kind of in details by Chalich and Feyron in 2018 and Arutyunov and Aleveci at 2019. So then, you know, I mentioned some of these papers several times, so you can find more references in these papers. Then there is a, you know, when we quantize these systems, there is a beautiful relation to Harish-Chandra theory. So something that we can call quantum Calogero-Moser chains. That's more or less so that also gives a quantum version. It's not in, I mean, it's more general, but in particular gives a quantum version of linearized systems of this type that were studied by Chalay, Fayron, and Aratyunov and Aleveci. And actually this subject is developing. So we have a paper with de Klerk. She's a graduate student at Ghent in Belgium, and Jasper Stockman, which is sort of a quantum version, kind of Q version of this. And in particular, the Q version of this quantum Q version. So yes, so then there is a connection to representation theory of MacDonald, theory, representation theory, and so on. So I said a few words about quantization. So yes, so then I probably should say that there is a universal version of these integrable systems. So just you can consider Poisson algebra of so-called chord diagrams on the surface. Those who are familiar with perturbation theory of quantum Chern-Simon theory, you know what a chord diagram is. So then it's the universal kind of Poisson algebra, in the sense that if you have G-colored chord diagrams on sigma, if you forget about G colorings, so then it gives chord diagrams on sigma, and then if you have any group and a subgroup, then the G prime chord diagrams, there is a homomorphism from here to here, and there are homomorphisms to here. In mathematics, such thing is called universal object. So there is a universal integrable system here. Of course, this notion is a little bit delicate in the sense that the spectrum, the number of independent elements here, here, and here is infinite. So one has to be careful to say, what does it mean to have a balance of dimensions? The beautiful thing is that the quantization of these systems is almost trivial. You just have to consider graphs in sigma across the identity. And this gives an infinite dimensional associative algebra that is filtered, and its associated graded is exactly the universal algebra of chord diagrams. And so you have a quantum superintegrable system in the same way. I don't want to go into details. The beautiful thing is that then one can use invariance, kind of combinatorial invariance, that combinatorial TQFT that we constructed with Turaev, use the operators corresponding to Wilson lines or Wilson graphs, and one can quantize all these systems. In the particular case, it was done by Artamonov and Shakirov a couple of years ago for the SU2 case, but they didn't know about superintegrability. So in fact, all these quantum integrable systems will be superintegrable unless for some special cases. One of these special cases is, well, this is definitely a special case, but it's more general. You can have as many punctures as you want when G equals 1. M is any. Anyway, so this is a separate talk. I just wanted to flash it. Thank you for the attention, and thank you for the questions.
Thank you for your talk. Very interesting. And let's thanks Nicolai. Unmute ourselves and thanks Nicolai. Now we have time for a couple of quick questions, and then we can turn off the camera and continue discussion. But if someone have something urgent to ask, please.
I would like to ask a question. So what about
Yes.
the elliptic halogen?
What about the halogen?
Oh, Jejina, hi.
Hello.
Oh, Jejina, hi. Hello.
What about what?
So the elliptic
What about what?
where are they in your,
You ask forbidden questions.
sorry,
You ask forbidden questions. Sorry for
So, okay, I will give a the answer. Sorry, I have an echo.
Sorry, I have an echo.
It's not me against.
Yeah. I identified and muted.
Oh, okay, good. So the elliptic case is well, it must be related. There is only one possibility. It cannot be obtained in the way how I did it using finite dimensional Lie groups. You really have to go to, you kind of have to do the same thing, but now G should be some kind of elliptic loop group. And so that's what I think. There is another question that you probably want to ask, but I'll jump ahead and we'll answer it. What is the connection to Hitchin systems? So again, I'm not quite sure what is the connection to Hitchin systems. They are different, but of course there is a connection. And I think since again we all know that elliptic Kaluza-Mozers can be obtained from the Higgs bundles, and these are Hitchin systems. So I think some combination of using, yeah. So I don't think if you will just use Hitchin systems, you will have sort of more interesting examples of superintegrable systems. But some kind of combination of this Higgs bundles with elliptic loop groups should work.
Okay, thank you very much.
Can I ask related but simpler question? So did you use somewhere real forms? For example, I don't know, trigonometric or hyperbolic Kaluza-Sutherland should be about choosing the real form, yes?
Yes, so I tried to hide this truth, but so now I can tell you. So
Should I stop the recording before you uncover some mystery?
What?
Should I stop the recording or it could go on?
No. It's not. It's a truth, but it's not such a dramatic truth that it should be hidden forever. So so just well, you know, if you are kind of true physicist, then whatever dynamical system you study should be real. It should be in some real phase space. But if you know enough mathematics, then, you know, like Evgeny, I'm sure you know enough mathematics, otherwise you wouldn't ask this question. So you can say the following, okay, I can analytically continue whatever real dynamics I have in the complex case, and maybe something good will happen. And in fact, something very nice happens in this case. If you consider G to be a complex algebraic group, then you know, you have nice kind of algebra geometric tools to handle this. So then if you have in mind physical applications, then all you have to do is you have to choose different real slices. And so everything that I was talking about can be done in complex algebraic case, but then at the end of the day, you really have to choose a real slice and to see what's going on there.
Yeah. it is essentially algebraic things like integral.
It's essentially algebraic. I mean, all the examples that I was talking about related to modular spaces, these are algebraic integrable systems of rather simple nature. The spectral curve is sort of trivial.
Yeah, thanks. Other questions?
Yeah, good question. Is this instant or moduli space a good example of superintegrable system? If I remember the ADHM construction, I think the functions of the say if I call the coordinates in situ x and y, the symmetric polynomials of the x positions of the instantons are commuting, and I think they also commute to the large subalgebra.
David, thank you for this question. I never thought about this, and actually, what is the reference that you mentioned? I didn't know.
I don't know for the references. So I was thinking about the ADHM construction of the space. I think it's easy to show that there are a bunch of commuting Hamiltonians, which I think are actually related to the spin calogero, the rational spin calogero system. And I think it's a superintegrable.
But by modular spaces of instantons, do you mean Higgs bundles? Modular space of Higgs bundles?
No, instantons in situ, like UN instantons in situ. It's an Keller modular space, so it's complex symplectic. And it has a whole bunch of functions. I think one can. Okay, we can discuss it in more detail, not in the question. Then sorry.
Yeah, I'll be happy to do this, but I unfortunately I have no answer.
Can I ask one question?
Yes.
So as far as I understand, so the situation is as follows. This is about this your basic notion superintegrability. So you start from symplectic manifold, then you have an algebra of functions. Then you pick up a certain subalgebra of it. You call it P2n, say, minus K.
No.
This subalgebra.
No, P2n minus K is a manifold. The subalgebra would be the algebra of functions.
Yeah. Subalgebra will be exactly. So there is a certain subalgebra. So let's talk about just Poisson subalgebra. So you pick up certain Poisson subalgebra.
Yes.
And if you look just at this subalgebra, it is degenerate. So there is a Casimir.
Yeah.
Or Casimir of it.
Yeah.
But of course, the number of Casimirs essentially depends what you choose, which subalgebra you choose.
Absolutely.
And my question is, the fact that you have superintegrability, namely this relation between ranks of these subalgebras, is it always possible to realize such a situation on a symplectic manifold, or it depends on the manifold itself? Not for any manifold you can find such a situation that you have these two subalgebras and this relation to each other. The ranks of them.
Let me first make a comment. So if you start with this Poisson subalgebra with the algebra of functions on P, so it's a very good remark. So superintegrability means that the center, the Poisson center of this subalgebra is maximal possible. Maximal possible in this symplectic manifold. In other words, if the subalgebra has the rank 2n minus k, then the center should have rank k. The center of the rank cannot be bigger than this. It can be smaller than this. Then you don't have the superintegrability. So again, it's some maximality condition. Whether any symplectic manifold has such structure, I don't know. It's a similar question to the following. When on a symplectic manifold, you have a Liouville integrable system. So in other words, geometrically, Liouville integrable system means that you have a Lagrangian fibration. So you have a Poisson projection to an n-dimensional manifold, and you require that the fibers of this, generic fibers of this should be Lagrangian submanifolds. I don't know if there's a theorem saying that every symplectic manifold has such vibrations. Or, I mean, see, it shows my education in symplectic geometry. My impression is that there are no such results, and that would be some kind of, so I don't know, I don't want to say something stupid. And having superintegrable system is a little bit more complicated. So it's more structures. So it's the same. I don't know. It's possible that not every symplectic manifold has such structure, but that would be some weird example, I think.
Yeah, thanks. Maybe at that point we will stop official part of the seminar. Kolya, can you turn off the recording?